congratulate everyone for selecting for the Statistics Special Degree. So in this semester you have to follow the Stochastic Processes 1 module as a special student. So today on I'm going to start lectures and I'll be uploading lectures as recordings so you can follow them, and I'll be taking some online sessions, right? So if you have any question, we can discuss those questions during the online sessions, right? So if you go to Cal, you may see I have already uploaded the module descriptor and some of the introduction materials, right? Basic, in order to give you a basic knowledge about stochastic. So I hope during the quarantine period you have gone through with all these documents, right? Maybe you didn't understand the lecture materials, but nothing to worry. I will explain you one by one. So first, if you look at the module descriptor, this is a compulsory course, right? And you can see the course outcomes, right? The learning outcomes, right? So at the end of this course you will be able to demonstrate the importance of the stochastic processes in every field, right? Including your day-to-day life, right? And also you should be able to construct appropriate stochastic models for such real-life situations, right? By giving good descriptions and presentations, right? And apply the concepts and the procedures that we are going to learn in this course. So if you look at the content, you will see the things that we are going to discuss throughout this course. So first we are going to discuss about the introduction to stochastic processes and general things in stochastic processes, and about the Markov chain, and about the classification of states and so on, right? So we'll see how it goes. I have already included some of the references. If you are going to follow, you can nowadays, because of this COVID-19, most of the reference books are available as online material, and so you can easily download them and follow, right? So then let us start the session. Right. So the first thing is, when it comes to stochastic processes and how do they fit in. So as you are statistics special students, by now you have a good knowledge about statistics, right? So throughout your first year and second year you have learned so many things in statistics. So actually when it comes to statistics, you need to have a foundation in statistics and also in probability, right? So basically we have so far you have learned two things. That is, you have learned some of the statistics concepts and you have learned some of the probability concepts. Alright, so the question is, why you learn statistics? So you learn statistics when you want to study about the randomness in patterns, right? Now for an example, if you take the Poisson distribution, right, and if you take the uniform distribution, right, so those things comes under statistics. And then again you have learned about probability, how to calculate the probability of a given event, the conditional probability, Bayes theorem, all this stuff. So if you are concerned about a process or event, in order to calculate or evaluate the randomness in a process, we use the probability concepts, right? So based on the based on the modules that you have studied in your first year and second year, by now you have laid the foundation for statistics and probability as well, because by now you have learned about the maximum likelihood methods and about the hypothesis testings and about the regression models maybe, right? So in this course, the question is what are you going to learn in this course, or what are you going to learn in Stat 41763? So I will give you some of the examples, right, that we are going to learn in this stochastic processes. So if you take this first example, let's say this is one of the very famous examples in stochastic processes, which is known as gambler's ruin, right? Maybe you have heard before. It's like this. Now you're going to toss a coin. So before you toss a coin, you are having some amount in your hand. Now let's say you're going to start with $30 and you're going to toss a fair coin repeatedly. So we know when you toss a coin, you will end up with either a head or a tail. So in this case, if you end up with the head, you will receive $5. That is you win if you receive a head. On the other hand, if you receive a tail, that is you are going to lose the game, where you have to pay $5 back, right? So when you are tossing the coin repeatedly, sometimes you will win, sometimes you will lose, right? So sometimes you will get $5, sometimes you will lose $5, right? So but at one point you have to stop the game, right? That is, you have to stop this under two conditions. One is you can stop the game if you have received $100, or else you can stop when you lose everything, right? So if this is something that you are interested, we can calculate the probability that you lose everything. Okay, so this is somewhere you can apply the stochastic processes, because when you read this question you can understand it's not a basic probability question that you have gone through so far, right? It's different. So you will see when you do the when you calculate this, you will get the answer as 70% or 0.7. So we will do the calculation. So I just want you to understand the concept, right? That is one of the examples that where you use stochastic processes. And the second one, this is also one of the very famous examples in stochastic processes, right? That is winning at tennis. That is, let's say you, what is the probability of winning a game of tennis starting from the even score? Right, so we call it as deuce, right? That is, when we know if you are going to play a tennis game, you need to have two players, right? So if these two players having an equal score, we call it as deuce. So if you are in a deuce state, right, okay, how you are going to win this game, right? So let's say if your probability of winning each point is 0.3 and the opponent's is 0.7, we need to find the probability of winning the tennis game by you. Okay, so we are in a place where you have equal marks. So when you have the next first game, there are two options. You can win the game or you can lose the game. If you win the first game, then you have to go to the second round, and if you even win the second round, that is, you are the winner. But if you lose the second round, again you are coming to this deuce state, right? And in the other hand, if you lose the first round, right, and if you lose the second round as well, you are going to lose the game. Or else if you lose the first round and if you win the second round, again we are coming to a deuce state, right? So you need to understand what's happening here. So here I have denoted. Now if you can see this picture, we are at this state, the deuce state. So if you win with probability, let's say P, you are ahead now. You are winning with probability P means if you take the opponent's losing probability as Q, so the opponent has lost the game. Now opponent is here, and the opponent lost the second game also with probability Q. Opponent will lose, but you will win. And if you come here now, if you win the first game and if you again win the second game with probability P, you're going to win. But when you have win the first game, if you lose it with probability Q, that is, you are going to the due state again. And here, if the opponent win the game with probability Q and again opponent lose the game, that is, you are winning with probability P, again we are coming to a due state, right? So this is also one of the examples. By calculating with these values, we can show that the answer is 15%. We'll see how will we get that. So this is where you can apply the stochastic processes, right? So the next example is winning a lottery. So let's say 1,000,000 people have bought tickets for the weekly lottery draw. Each person has a probability of 1 in a million of selecting the winning numbers. So if more than one person selects the winning numbers, the winner will be chosen at random from all those winning with matching numbers. You watch the lottery draw on TV and your numbers match the winning numbers. Only a 1 in a million chance, and there were only a million players. So surely you will win the prize, right? So what is the probability you will win? Now what will happen? Here there are million people and they all are buying tickets, right, for a weekly lottery draw. So the probability of selecting a lottery with winning numbers is 1 in a million. Okay, so if so many people have received these winning tickets, what will they do? They are giving the prize only to one person, so they take all the people who have received the winning numbers and then they will choose a person at random and will give the prize. So since there are 1,000,000 people and since the probability of receiving a winning ticket or the winning numbers is also 1 in a million, you may feel like if you have received the winning numbers in your lottery, you are definitely going to get the prize. But actually it's not the case, right? So you will understand when we are doing the stochastic processes why it's not the case. So actually we can show, if you do the calculations using the stochastic concepts, if you have received the winning numbers, the probability of winning the prize is equal to 63%, or in other words 0.63, right? So we will discuss this case as well when we are learning the stochastic processes. If you go to the next example, this is also one of the very famous examples which is known as Drunkards War. So in that case, what we do is, let's say a person is drunk, okay, and that person straddles to left and right as he walks along. So what will happen? With each step he takes, he straddles one pace to left with probability 0.5 and one pace to right with probability 0.5. Right? So we want to find out the expected number of paces he must take before he ends up one pace to the left of his starting point. Okay, so we will discuss this one as well. So did you understand the question? That is, there is a person who is drunk, so he can straddles to left and right. So the probability of straddling to left is 0.5 and to right is 0.5. So we are going to find the expected number of paces he must take before he ends up one pace to the left of his starting point. Right? So he staggers to left and right, but eventually he will arrive to his home, right? So we are going to find out the expected number of paces he must take before he ends up one pace to the left of his starting point. Okay, so that one also we are going to discuss. And this is also one of the famous example, that is the pyramid selling scheme. So if you have heard about this, it's also a bit famous in our country, but actually it's not a legal thing, it's illegal, right? So let's say you have received a chain letter like this, and you have to send $10 to the person whose name comes at the top of the list, right? And send the letter to as many people you can within a few months. The letter promises you will have received $77,000 in $10 notes. Will you? Right? That is, you will get a chain letter. When you receive a chain letter, there are some names and in this letter, and you are going to send few letters to another set of people. Sorry, you are going to send a letter. Send $10. You are going to send $10 to the person who's having the name at the top of the list, right? And then you are going to, you're going to do, you have to add your own name to the bottom of the list and send the letter to as many people as you can, right? So in this case, you are only spending $10, but they guarantee when the other people also receive their letters, if your name is at the top of the list, they will send you $10. So you will get $77,000 in return by just spending $10, right? So this is the concept, this is how they sell these stuff, but actually it depends, right? It depends on the response rate. Now, even though you are going to send letters to other people, if someone else received the letter, we can't guarantee that one will do the same, right? So sometimes chain will get sometimes chain will break. So if the chain is broken, you can't expect anything back, right? So there is a probability, right? Then if you make the assumptions about the response rate, right, we can expect $76 back, but it's also with a probability of 0.64. Okay, we'll discuss how this thing is happening. And the next thing is the spread of SARS. So actually we can talk about spread of COVID as well. So you can see, if you look at this figure, SARS was very famous in Singapore, and you can see this figure, how the disease is getting spread, right? So this was in 2003. So if you observe the pattern of infection, what is the probability that the disease eventually dies out of its own accord? Right? So we can do the same thing. If you observe the spread of COVID-19 in Sri Lanka, right now it's almost coming to an end. So we can calculate, if you observe the pattern and the spread, we can calculate the probability of the disease or probability of COVID that eventually dies out its own accord, right? So if you use this information, we can show it as it's equal to 0.0997, right? So then another example I would like to go through, because here in this course we are going to discuss about the Markov chains in the future. So when it comes to the Markov's marvelous mystery tours, right, this is not about Markov chains, but in this case what we do is there is a company who do tourism, and all the stochastic tourist experience for the town, they come to this Rotorua town and they want to experience some of the stuff, right? And they have 8 tourist attractions in this city, right? So this person will take his clients completely at random with the probability shown below in the figure to each place, and he has promised to his clients that at least 3 exciting attractions per tour, and ending at either the Lady Knox or the volcano. But unfortunately he makes no mention of how the helpless tourists might get home from these places, right? So what is the expected number of activities for a tour starting from the museum? That is, you are going to, every tourist is going to start from the museum, and they can go to this cruise, and they can go to have a look about this helicopter or the village or the flying fox, hangi, geese. There are so many places. You can see, if you observe the figure, there is a probability of visiting cruise from museum, that is 1/3, right? So likewise we know the probabilities, but the thing is, the tour guide has promised the tourists, their clients, to show at least 3 places, and also they are going to end the tour from geyser or from volcano, right? So when, if you come to geyser, you are not going to visit any other places, you are going to end up the tour. And if you come to the volcano, you are not going to visit any other places, you are going to end the tour. So we need to find out the expected number of activities for a tour starting from the museum, right? Because there may be different paths. For an example, one can start from museum, then one can go to cruise and go to the village, then go to the hangi, and then go to the geese. Or one can go start from museum, cruise, village, again back to cruise, and then flying fox, and then hangi, and then helicopter, or and then volcano. Likewise, there are different paths, but we need to find out the expected number of activities for a tour starting from the museum. So these are the examples, these are the concepts, or these are the places or the real life situations where you can apply the stochastic processes, or the concepts of stochastic processes, which we are going to discuss in detail in the upcoming sessions. Okay, so if you look at the course, of the structure of the course, we are going to discuss about the probability. Actually, you have already learned about the probability, random variables, and the distribution so far, but I'm going to quickly go through all these things, right, in order to remind you the stuff. And you have to remember this: when you are learning stochastic processes, the probability concepts are very important. You can't just forget, and you can't just clear your mind and learn this module as a very new one, right? Because we need all these concepts you have learned so far to apply to these stochastic concepts. Okay, so we are going to talk about expectation, the generating functions, branching processes, and Markov chains, right? So here today, when you take the first one, chapter 1, we are going to discuss a quick revision of the sample spaces and random variables, and the formal definitions of stochastic processes, right? So this one will be very easy, because all the things that you have learned so far will be refreshed again, right? So then let's start quickly. Let's start our quick revision. So we are going to discuss about the sample spaces and the random variables, right? So if you can remember, what is a random experiment, right? Basically, if you are doing an experiment, if you are conducting an experiment, and if you cannot predict about the outcomes, we call it as a random experiment. So what we have done in our past modules is when you are learning about the random experiments, the sample space is something very important. That is, when you are doing a random experiment where you have no idea about the outcomes, right? But if you observe all the outcomes of that random experiment, and if you write it as a set, we call it as the sample space. So the basic example is tossing a coin. So when you toss a coin, we know sometimes we may ended up with the head, or sometimes we may ended up with the tail. We never know. Right? So in that case, what we can do is if you anyway, we know we will end up with only these two results, that is a head or a tail. So we write the sample space as head and tail concerning this experiment. So when it comes to a random variable, we know the random variables are denoted by capital English letters, right? So if you take random variable x, it is defined as a function from the sample space to real numbers. We know when you take a random variable, what we do is we have a sample space of a given experiment, and we are going to map all the results or the outcomes of that sample space into a real number set using these random variables. So when it comes to random variable, so it assigns a real number to every possible outcome of your experiment, or every possible outcome of your sample space. For an example, now when you take the experiment of tossing a coin, our sample space consists only two outcomes, head and a tail. So in that case, we can tell, or we can map this head to 1 and tail to 0. That is, when you ended up with the head, we write 1 instead of writing head, and we write 0 when you ended up with the tail without writing tail, right? So here, in that case, when you write your sample space, you have 1 and 0 in your sample space, okay, not characters. So what you have to do is you have mapped the outcomes to real numbers, right? So actually a random variable is a way of producing random real numbers into your sample space. So when it comes to a stochastic process, the stochastic process is a family of random variables you have, right? When you take this stochastic process, in the stochastic processes you have so many random variables. It's a collection or a family of random variable. But also in stochastic processes, we are always very concerned about the time. So when it comes to stochastic process, and when we denote the random variable, that's why we are using this notation. You can see x within brackets, I have used t, right? Where t is your time index. So since this random variable is depending on time, you have to use the time index. Okay, so we can say, if x is a random variable, I have used xt to denote the stochastic processes where t belongs to time, right? Where t usually denotes time, that is, at every time t is the set, in the set capital T, a random variable xt is observed, right? So that is, if you take, for an example, if you take a day, and if you are going to observe this random variable x by keeping 1 hour distances, right? So that is, let's say you are going to start the process at 8 a.m. So when t is equal to 8 a.m. you can observe x value, and then when t is equal to 9 a.m. again you can observe x value. Likewise, at every time t you have a specific value for this random variable, and that collection you call it as a stochastic process, right? So actually when you take a stochastic process, we basically divide stochastic processes into two parts. That is, we have the discrete time processes and we have the continuous time processes. So what is this discrete time processes and what is this continuous time processes? So if the set T is finite or countable, you call it as a discrete time process. Right? So you can see, if you look at the example, if you are going to observe the value at x0, x1, x2, x3, right, at discrete time points, these are countable and finite, then we call it as a discrete time process. That is, for an example, you are going to observe, let's say every hour we can observe happening of some incident, right? So you are taking the count of every hour, right? Let's say in between starting point and the next hour, nothing can happen. So if that is your case, we call it as a discrete time process. And from the other hand, when it comes to a continuous time process, that is, when you take the time index, it can take any value. It can take it from 0 to infinity, it can take any value. Or if you have a specific time range, let's say t is 0 to k, that is the specific time range, but in every instant you can observe the random variable. Okay, that is, for an example, if you are going to observe the number of customers who are visiting to a particular bank, right, let's say from 8 a.m. to 12 noon you are going to observe. So sometimes there may be no customers at 8:30 a.m. but that is a possible value. Even though when you observe no customers were there at 8:30 a.m., there is a possibility to get customers at that time, right? So that is within the time range. At every instant in time, there is a possible observation of the random variable. So if that is your case, we call it as a continuous time process, right? So you can see here I have put a note, that is, xt need not change at every instant in time, but it is allowed to change at any time. So sometimes, even though you didn't observe that, there is a possibility, as the example of the bank, the number of customers, sometimes there were 0 customers at 10 a.m. in the bank, but there is a possibility to get customers at 10 a.m. right? So we call it as a continuous time process. Then there is another terminology when it comes to stochastic processes, that is the state space. So the state space is the set of real values that xt can take. So xt is our stochastic process, or the random variable that we are going to observe in our stochastic process. So it can take values, right? So we know every xt take a value in our real number set. So when it comes to the state space, which is denoted by s, will often be smaller set than the real numbers, right? For an example, if you take xt is the outcome of a coin tossed at time t, then the state space is 0 and 1, right? The real values that we can take for your random variable. It's just like the sample space, right? So if the state space is, we call it as discrete if it is finite and countable, and if it is infinite, we call it as continuous, right? So the state space is the set of states that the stochastic processes can be in. Okay, so when it comes to the state space, we have all the possible states that the stochastic processors can be in. So it's actually like your sample space. Okay. So as I said, this is a quick revision of what you have learned about the random variables. So I hope you have learned about so many distributions by now. So you need to have a good understanding about the distributions that you have learned so far. So one thing is the binomial distribution, right? So we know in the binomial distribution, what we are interested is the number of successes, right? So you have n trials, and if the probability of a success is p, we are counting the number of successes in the binomial trial. So in that case, what you have to do is you should know what is the probability function in the binomial distribution, that is ncx p to power x 1 minus p to power n minus x, where the number of successes or x can be 0 or x can goes up to n, that is the sample size. And I hope when you are learning about the binomial distribution, you have learned the mean or the expected value of the binomial distribution, that is NP, and the variance is NP times 1 minus P, or you can write it as NPQ, where Q is equal to 1 minus P. So the proof of the mean and variance, those things we do not have to memorize, or you do not have to by heart for this course, but you should know what is the expected value and the variance of the binomial distribution, right? And also, if you have a random variable x with binomial distribution with n trials and p probability of success, and another random variable y again with binomial distribution with m number of trials, but the probability of success is the same, right? So two different random variables with the same probability of success, but you have two different number of trials. In that case, when you take the addition or the summation of these two random variables, again we can see it's also having a binomial distribution. The total number of trials would be n plus m, and the probability of success is the same. And then the Poisson distribution, this is not Poisson, right? So don't get Poisson. So this is Poisson distribution. So when it comes to the Poisson distribution, we know what we are interested is about the number of incidents that can be happened in a given area or within a given time range, right? That's what we do in the Poisson distribution. So there we know we are interested about the average rate, okay, which is denoted by lambda. So when it comes to the Poisson distribution, the probability function is given by e to power minus lambda, lambda to power x divided by factorial x, where x can start from 0, that is for a given area or for a given time length, there can be 0 events, or it can goes up to infinity. And we know the Poisson distribution is a very special distribution where we have the same expected and variance value, which is equal to this average rate, that is lambda. And if you have Poisson distributions, let's say you have a random variable with a Poisson distribution with rate lambda, and another random variable y with the Poisson distribution with rate mu, and if x and y are independent, right? This is true for the binomial distribution as well, for the summation of the binomial distribution as well. Your random variable should be independent. Then when you take the summation, that is also having a Poisson distribution, and when you calculate the rate is equal to lambda plus mu, that is the summation of the two rates values, right? And then I hope you have learned about the geometric distribution as well. So in the geometric distribution, what we do is we are concerning about the first success. That is, we are counting the number of failures that we have to face, so that number of failures that we observe up to first success in a sequence, right? So in that case, sometimes when we do our experiment at the first instance, we may ended up with a success. So in that case, you have 0 failures, right? Or maybe you are getting 1 failure and then the success, or 2 failures and then the success. So it depends. So since we are counting the number of failures, so when it comes to the probability function, you can see x can be 0, 1, 2, it can goes up to infinity. And then when it comes to the probability function, it is this, that is 1. You take p as the probability of the success. Since you have 1 success, that probability is p. Since you have x number of failures, we can take the probability of failure is 1 minus p, if p is the success probability. And since you have x number of failures, you have the exponent as x here. So when it comes to the mean value of the geometric distribution, right, it has the expected value is 1 minus p over p, or simply you can write it as q over p, where q is 1 minus p, and the variance value is 1 minus p over p squared, or you can write it as q over p squared when q is equal to 1 minus p. And in this case also, if you have independent, let's say if you start, you have x1, x2, x3 up to xk, k number of independent random variables, and each random variable is having a geometric distribution with the probability of p. And then if you take the summation of the random variables, they are having a negative binomial distribution with the same success probability p, but here you are having k number of successes, because in each random variable you are having a 1 success, and since there are k number of variables, you are observing k number of successes. So because of that, when you take the summation of a geometric distribution, it's following a negative binomial distribution, right? And then when it comes to a negative binomial distribution, so in negative binomial distribution, we know if x is a random variable which is having a negative binomial distribution, we denote it as kp. So that is, we count again the number of failures before k success, right? That is, until we receive k number of successes, we are counting the number of failures. For an example, if you are tossing a coin, until you receive a head, that is a geometric distribution, because as soon after you receive a head, you stop your process. But if you are tossing a coin until you receive 5 heads, so you keep on tossing your coin until you receive 5 heads, right? So that is a negative binomial distribution. So if you are tossing a coin until you receive k number of heads, you can count the number of tails that you have received so far. So that is the random variable in negative binomial distribution. And there we have, so if you look at the probability function, since you have k successes, here you have p to power k, and since you have x number of failures, 1 minus p to power x here. So in between these successes, the failures can be happen anywhere, right? So if you take all the number of trials, we know we have k plus x number of trials, right? So before the last one, at any other places, the failures are possible. That's why we have subtract 1 here, and this k plus x minus 1 cx, that this combination, this combination value gives you the number of possible failures, right, up to kth success. And in that case also we know when it comes to x can be 0, 1, 2, any number of failures are possible. So when it comes to the expected value of a negative binomial distribution, you have k times 1 minus p over p, or you can simply write it as kq over p, where q is 1 minus p. And when it comes to the variance, you have k times 1 minus p over p squared, or you can write it as kq over p squared, where q is 1 minus p. See, if you just compare the mean values and the variance of the negative binomial with the geometric, so only small change, because since in the negative binomial you are interested with k number of successes, if you take the mean of the geometric, it's q over p, and you have multiplied that by k when it comes to the negative binomial. Same thing has happened in the variance. In the geometric you have q over p squared, and you have multiplied that by k when it comes to the negative binomial distribution, since we have k number of successes. So in this case, if random variable x is having a negative binomial distribution with the parameters are k comma p, that is, you are observing k number of successes, probability of success is p. And again, when you take the random variable y, it's also having a negative binomial distribution with m number of trials, with m number of successes, where the probability of success is p. So if these two are independent, when you take the summation is also having a negative binomial distribution, where you are observing k plus m number of successes with success probability p, right? So in this case, we're going to discuss about the next distribution, that is the hypergeometric distribution. So in hypergeometric distribution, we know we have a big population where you have successes and failures, right? And we are going to draw a sample from that big finite population. So for your sample is also consisting failures and successes. So here what we are interested is number of successes in a sample. So if the sample size is simple n and the population size is capital N, and the number of successes in our population is denoted by capital M. So if you take x is a random variable with hypergeometric distribution, n is the population size, capital M is the number of successes in the population, and simple n is the sample size. Okay, so we are interested, x is the random variable, interested in the number of special objects, so the successes in a sample. So if you are going to draw a sample of simple n from a finite population of capital N, in that case you can write the possible combinations, or all the possible ways of selecting a sample of size n from a population of capital N as n over n, capital N C n, right? So this is the all possible ways to select a sample of size n from a population of capital N size. But we know in the population we have capital M number of successes. So if you take the number of successes in your sample as simple x, to get simple x number of successes from capital M, you can find all the possible ways from MCX. And if you take the number of failures in the population, that is n minus m, right, n minus m is the number of failures in the population, and in your sample, since you have simple x number of successes, n minus x number of failures are there. So the possible ways are n minus n, m, c, n minus x. So this will give you the probability of receiving x number of successes in your sample. So when it comes to the expected value and the variance, that is expected value is m over n and the variance is expected value is np, where p is m over n. Variance is np into 1 minus p times n minus n over n minus 1. Again, p is m over n. So we know when it comes to the number of successors in your sample, sometimes we may end up with 0 successors, and sometimes if when you are observing the successes in your sample, sometimes you may receive when you observe the sample, sometimes all the values, all the observations in your sample can be successors. In that case, x can be equal to simple n. Okay, but if your number, let's say you are going to select a sample of size 100 and your population size is equal to 1000. Okay, but in the population, if you have only 10 successors, the maximum number of successors that you can select into your sample is 10, even though your sample is having 100 outcomes. So because of that, in that case, the maximum x value is equal to capital M. So because of that, the maximum x value can goes to sample size or the number of successors in the population, minimum from these two. It can be minimum from these two. Okay, right. And then when it comes to the next distribution, that is the multinomial distribution. So this is a bit different than the other distributions, right? So we say if we have a random variable x where x1 up to xk is multinomial with n observations and p1, p2, pk are the probabilities. That is what there are n independent trials, each with k possible outcomes. And if you take pi, right, that is if you take p1, that is the probability of outcome 1, right? Then we take x as x1, x2, xk, where xi is the number of trials with outcome I. So in this case, the multinomial distribution, we know the probability function is denoted like this, right? So we know when it comes to the, if you observe the marginal distribution, so if you observe x1, x2, x3 separately, they are having a binomial distribution. It's like this. For an example, if you have a paper with MCQ questions only, let's say you have 10 MCQ questions. Alright, so there you are going to observe about the number of correct questions. So each question is having a probability to get the correct answer or the wrong answer. Let's say the probability of getting a correct answer for question number 1 is 0.6. So here P1 is 0.6, right? For the second question, if it is 0.4, P2 is 0.4. So you will ended up with different combinations here for x. Sometimes, let's say, first 5 questions are correct, the second 5 questions are wrong. Or you can get a combination like correct, wrong, correct, wrong, correct, wrong, likewise. So here we observe that in multinomial. So when you take one question, we know it can be correct or it can be wrong. So it's a binomial distribution, right? So in that case, it's having a marginal distribution. It's having a marginal distribution for each xi, binomial marginal distribution, right? So when you take the mean value, that is denoted by npi, variance npi into 1 minus pi, because these are having binomial marginal distributions. And when you take the covariance of any two observations xi and xj, where these two are different, right? The covariance we can write as minus NPI into Pj. Okay, so the things that we discussed so far is all about the discrete random variables. So I'm sure you have learned about the continuous random variables as well. So when it comes to continuous random variables, the most basic continuous random variable is the uniform distribution. So in uniform distribution, you strictly have a range there. So, and the values or the observation between that range is a constant. So when it comes to the probability density function of the uniform distribution, we can write it as 1 over b minus a. And in that case, if you are going to calculate the probability of let's say receiving a value for this random variable which is less than for a given value, let's say the probability of x, where x is less than or equal to simple x, where the simple x is a value in between a and b. Okay, so in that case, what you have to do is with the by using the probability density function, you can find out that value, right? When you substitute x into this one, you can when you substitute x into your probability density function, it will gives you what you have to do is first you have to take the probability density function and then you have to find the cumulative distribution function. So with the cumulative distribution function, you can calculate the probability for the random variable where it is less than or equal for a given value. So capital Fx is the cumulative distribution function of the uniform distribution, which is equal to x minus a divided by b minus a. So if you are interested about this probability, you can directly substitute the value for the cumulative distribution function. And when you take the mean value and the variance of the uniform distribution, you can see the mean value is a plus b over 2 and the variance is b minus a squared over 12. And when it comes to the exponential distribution, so let's say a random variable x is having an exponential distribution with the rate lambda. So in that case, we can write down the probability density function as lambda times e to power minus lambda x, where x can take any value between 0 and infinity, that is x is always positive. So the cumulative distribution function for the exponential distribution is 1 minus e to power minus lambda x. So mean value is 1 over lambda, variance is 1 over lambda squared. And when you have a set of random variables which are independent, and if each random variable is having exponential distribution with lambda, then if you take the summation, we can say it's having a gamma distribution with these two parameters, that is k is the number of variables you have and lambda is the rate of the exponential distribution. So when we discuss about these two continuous random variables, why I have mentioned about the cumulative distribution is, now in the future topics, right, the coming up sessions, we are going to discuss about how to generate the random variable. That is also very important in stochastic processes. So when you want to generate random variables, this cumulative distribution function is something essential, right? We need to know the cumulative distribution function, but you don't have to by heart the cumulative distribution functions, because we will, when we know the probability density function of a given random variable, we can easily integrate that and find out the cumulative distribution function. So no need to by heart. And then we know another two important functions that you have learned so far is the gamma function, gamma distribution, and the normal distribution. So when it comes to the gamma distribution, so you have, when you take the x value, again x can take only positive values, and you have this probability density function, right? And in this, the tau k is the gamma function, and the tau k you can write it like this. And but when it comes to the cumulative distribution function of the gamma distribution, it does not have a closed format, so we are not interested about the cumulative distribution function of that. Same with the normal distribution. In the normal distribution, cumulative function is also not having a closed format, so we are not interested about the CDF of the gamma and the normal distributions, but we are interested about the CDF of uniform and the exponential distribution. So when you take the mean value of the gamma, that is k over lambda, variance is k over lambda squared, and if you take n number of random variables which are independent and each having gamma distributions, and then when you take the total, you can say it's also having gamma distribution, and the parameters, the first parameter you can take as k1 plus k2 plus up to kn, comma, here you can take the rate as lambda. And the very famous and very familiar distribution to you, that is the normal distribution, every day that you are using in statistics. So we know if x, random variable x, is having a normal distribution with parameter mu and sigma squared. Mu is the mean and the sigma squared is the variance, and this is the probability density function. And we know very well the mean value is mu, variance is sigma squared, and we know when you have n number of random variables which are independent, each having a normal distribution with mean mu I and variance sigma I squared, then when you take the summation, again we can observe a normal distribution. To calculate the mean, you can take the summation of the mean values, and to calculate the variances, you can take the summation of the variances, right? So just to quick show you the probability density functions we discuss, you can see the first one, the uniform distribution. As I told you, you have a strict range, and within that range you have a constant value in the uniform distribution. And when it comes to the exponential distribution, you have only one parameter lambda, right? You can see how the exponential distribution is changing with the parameter lambda. That is, when your lambda is a high value, you can see the tail is not that long, right? When lambda is equal to 1, you have a longer tail than when lambda is equal to 2. And when it comes to the gamma distribution, again you can see how your distribution is changing due to the parameters, right? When you have the same k value, but when you change the lambda values, you can see when the lambda value is small, the spread is you have a wider spread there, right? And then of course you have again the normal distribution with the same mean, but here we have changed the standard deviation and have observed what's happening. So same thing, when you have a big value for the standard deviation, that is, you have a big range for the distribution, right? So you have longer tails. So these concepts, what you have already learned in your first year, second year, so I just wanted to give you a quick revision, because we need all these concepts, right, in order to discuss about stochastic processes. So I think what we discuss in this first session is clear. So if you have any questions, you can directly send them to Cal, or you can send me an email. My email address is harshana.kln.ac.lk, right? Or else as y'all are the special students, I hope that we will be able to meet soon, and we will take the online sessions as well to discuss about the questions. So we'll end up this session for now. Thank you very much. I hope you all understand. Thank you.